Hi, in this video, we will first derive the formula for rotational inertia of a uniform solid sphere around an axis passing through its center by integrating r squared dm and get I equal to 2/5 mr squared. Then we generalize the formula for rotational inertia of any round object of mass m and outside radius r around its axis of symmetry as beta mr squared by introducing the parameter beta. Beta is different for different objects, and as you will see in the next videos, it plays a central role in the acceleration of a round object rolling down an incline. It is in fact the fraction of the rotational kinetic energy to translational kinetic energy of a rolling object. The value of beta is 1 for a ring, for a uniform solid cylinder or disk is 1/2, for a uniform solid sphere is 2/5, and for a spherical shell it is 2/3. So if you want to do a sphere, let's say this is a sphere. Because we know about disk or cylinder, we can divide this sphere into disks, and for each one use the disk equation and then integrate. Let's say this is the axis of rotation, we call it x, we call this y, and then take disk. The disk is like this. So this is dx, and it has a mass dm, and this distance is x, this distance is r, the radius of this disk that we cut through. And the radius of the sphere is capital R. And what's the relationship between r and this r with x? Then this is also r, right? Or you can call it y if you want. Let's call it y, which is the radius of the disk. Okay, so you have x squared plus y squared equal to r squared, right? That's the equation of the circle. X squared plus y squared equal to r squared. So y squared is equal to r squared minus x squared. So you can write y in terms of x. Right? So y in terms of x is this. Y is the radius of the disk. R is the radius of a sphere. And now you can write the I total integral of di, or I for this one, which is 1/2 y squared dm, right? Because it is like a disk, right? It has 1/2 its mass times its radius squared. This is 1/2 its mass times its radius squared, right? And now we can write y squared as all r squared minus x squared. But what is dm? We need to write dm in terms of dx and y and x. How do we do that? That's the tricky part in each of this integration. The hardest thing is to come up with that differential. If you come up with that differential, then everything will be simple. Okay, what is that? dm over dv is the same as total mass over total volume, which is 4/3 pi r cubed. Right? The same proportion of the volume, it has mass. So what is dv for this one? If it has a thickness dx, what is the volume? So dv, volume of this disk, is the thickness times the area, right? Means the area times dx. The thickness is dx, the area is a, right? What is the area? Is pi y squared, right? So it becomes pi y squared dx. And put that in here, so dm is equal to m over 4/3 pi r cubed times dv, which is pi y squared dx. And pi cancels out. This 3 goes up, becomes 3m y squared dx divided by 4 r cubed. That's the m. So I becomes 1/2 integral y squared times dm. dm is this, and 3m y squared dx over 4r cubed, and put everything that's constant outside. I becomes 3/8, right? 3/8 integral, sorry, m and r cubed also come out, m over r cubed. Right? 3/8 m over r cubed, then we get integral of y squared and y squared, y to the 4th dx. What is y to the 4th? Is r squared minus x squared squared, right? So I will be 3/8 m over r cubed integral of r squared minus x squared to s squared dx. And what are the limits of x? What are the limits of x? To cover all the masses goes from negative r to r, right? So negative r to r. Again, you have an even function over symmetric integral. Can I just put a 2 here and take from 0 to r?
Yes.
So I becomes, if you put double it, it becomes 3/4 m over r cubed and integral from 0 to r of r to the 4th plus x to the 4th minus 2 r squared x squared, right? And I also raised to the 2nd power dx. It's a polynomial integral, right? All right, so we take 3/4. We take integral of each term. What is the integral? 0 to r to the 4 dx. Becomes rx, then x becomes r, then r to the 5. So we get r to the 5th for the first one. For the next one, we get the x to the 5th over 5, right? The integral of x to the 4th dx becomes x to the 5th over 5. And then put 0 and r becomes r to the 5th over 5 plus 1/5 of r to the 5th minus 2r to r squared. What is that? The integral of x squared becomes x cubed over 3, right? So it becomes r cubed over 3. So this is the integral. So what is the result? Now I becomes, you see all of them have r to the 5th, right? Comes over, cancels the r cubed. You have 3/4 m r squared times, you get 1 here, plus 1/5 minus 2/3. Right, I just factored r to the 5th and canceled r cubed. What do we get here now? If we do common denominator, 5 and 3 is 15. I is 3/4 m r squared. I make all the same denominator. 15 over 15 and plus 3 over 15 minus 10 over 15. Minus 10 is 5 plus 3, 8 over 15, right? So I becomes 3/4 times 8 over 15 m r squared. So this gives you a 5, this gives you a 2, right? So I becomes 2/5 m r squared. So if you go to the book, you see that I is listed as, for a sphere, for a solid sphere, is 2/5 m r squared. For a cylinder, it's 1/2. For a ring, is 1. And for other objects, depends on what the shape is. But for rolling objects, usually we have these 3. And if you have a spherical shell, means that a sphere that is hollow and only has a thin spherical shell, it becomes 2/3 instead of 2/5. So for the spherical shell, it's a little bit different. All right, so let's review all of this. These are very important. You don't need to worry about deriving these formulas. I just wanted to have them to show that everything comes naturally from math. There's nothing mysterious here. The rotational inertia I, object, and I. So for ring, has mass m and radius r, we have mr squared. For cylinder, we have 1/2 mr squared. This also is a cylinder, has mass m and radius r. For a sphere is 2/5 mr squared. 2/5 is 0.4, right? This is 0.5, this is 1. In general, it is a factor times mr squared. For any rolling object, is a factor, you see the factor in front of him, times mr squared. So I like to call that factor beta times mr squared. So this beta for a sphere is 2/5, for a cylinder is 1/2, for a ring is 1. Okay? For different objects, different. And why is that? See, we said that the ring has all the mass as far as they could be, so the factor in front of it is 1. But in a cylinder, the mass is distributed uniformly from the axis to the edge. It gives you a factor of 1/2. But if you look at a sphere, look at the sphere. Any axis that you take, there's more mass closer than farther away. That gives you a smaller factor than 1/2. That's cylinder. Okay, so the closer the mass is to the center, to the axis of rotation, the smaller this value is. Right? This is about 600 grams, but the discs are only 60 grams. So 90% of the mass is within the radius of 1.25 centimeter. Very, very small. I measured it. A little bit of mass is far away. That's why this was the fastest. So remember, this was the fastest, almost as fast as the car. All right, now let's see how we can find the actual acceleration of the objects. I hope you enjoyed this video. Thanks for watching.